This video we will discuss frequency response function. What is frequency response function? Frequency response function basically is a tool that we will use later on to help us in designing and optimizing controller for our system. We will discuss first what frequency response function is. Let me pop up this slide again. I think I have already shared this drawing a long time ago when we discussed dynamic system. So in general, then, if I have a dynamic system, any dynamic system, it should have a property tagged to the system which is referred to as a transfer function. So let's consider now here we have a system where the transfer function is equal to GS, and if to this system we give an input XS, then the output will be equal to XS times GS. Remember, all of these things are discussed in Laplace domain. Okay, so if it is in Laplace domain, then this simple relationship will apply. Now let's consider again to this system with this transfer function of GS. I will apply a harmonic input. Just as an illustration here, let's consider a cosine function as the harmonic input. This input has an amplitude of A, the frequency of omega, and it has a phase lead of phi here. Okay, so it's a cosine function with a frequency of omega. Referring to this trigonometry identity where cosine omega t plus theta is equal to cosine omega t times cosine theta minus sine omega t sine theta, I can rewrite this input function xt into the following form, right? That's pretty straightforward. And then in order to analyze the output of this system due to this input, I first have to convert this xt in Laplace domain. So referring to the Laplace table, the Laplace of cosine omega t is equal to s over s squared plus omega squared, where the Laplace of sine omega t is equal to omega over s squared plus omega squared. Then this xt, the input to this system GS, will be equal to this in Laplace domain. Okay, and then moving forward, then I can analyze the output of this system in Laplace domain, which is just simply equal to XS times GS, where GS is known, for instance, in here. Okay, I can rewrite again. I can manipulate this equation here by factorizing the denominator here, s squared plus omega squared. I factorize it into two simpler form of s plus j omega times s plus j omega. Okay, so in this case I assume that this the root of this denominator is or are complex number. Okay, and then what I'm going to do, if we want to convert the output ys back to the time domain to yt, what we have to do, we have to perform partial fraction expansion. The partial fraction expansion of this ys will look like this, where the first two terms are associated to the denominator that are originated from the input xs, where the coefficient for the first term is, for time being, let's call it k, and the coefficient for the second terms is k star, while now the remaining terms here from the third term here, the denominators are associated to the denominator of gs, denominator of the transfer function of the system. Okay, at this point I think it's still clear enough. Now let me show this illustration again here. I have a dynamic system where the red one here is the input to the system, the green dashed line here is the output of the system. So the red is the input, the green dashed line is the output. To this dynamic system, I give a harmonic input, and then the response looks like this. We have already discussed before that the response of dynamic systems can be classified into two regions, the transient region and the steady state region, where at the steady state region the response becomes steady. The response will tend to follow the input. So if you look at this, when the input is harmonic in a steady state condition, the response is also harmonic, which doesn't happen at the transient region. At the transient region, everything is still not stationary, right? It's still varying in time. So in this case, then I can intuitively say that the first two terms of my response here are associated to the steady state response, because these two terms are associated to omega here, where omega is the main parameters of this input, a cosine omega t, right? So these first two terms are associated to the steady state response, while the remaining terms here are more associated to the transient term, right? If, let's say, now I'm only interested in the steady state response, so what I have to do, I will just have to focus more on these two first terms, because these remaining terms are the terms that are associated to the transient response, right? So now moving forward, I'm only interested in the steady state response, so I will take a closer look on these first two terms. In order to solve the steady state response, the steady state of ys, what I have to do then, I have to solve these partial fraction expansions, which means I have to find the k and k star accordingly, right? So how to find k? You just have to refer, if you need to refresh again your memory, you just have to refer back to your math. In order to find the coefficient k, what we have to do, we have to multiply the function ys here with the term, where the term here is equal to the denominator of the term that is associated to this parameter k, the parameter that we want to find, the value. So I will multiply ys with s minus j omega, and then next what I have to do, I have to substitute all of the s's here with j omega. Okay, you know how to do this partial fraction expansion. So because of this s minus j omega will cancel this s minus j omega. This is what I will get, And then the last step, I just have to substitute j omega to all of the s's here. At the end, this is what I will get. Okay, I can cancel all of this omega here, and this will be my k, right? Or I can simplify this form also. I can rewrite this k into this form, right? This is pretty straightforward. I just cancel the j here and then multiply it with j for the second term here. So this is my k. I can substitute this to this value here. I can rewrite this again into this form, because as you know, exponential of j phi is equal to cos sinus phi plus j sinus phi. So I can rewrite this into this form. Similarly, I can also find k star. I can take the same steps, exactly the same steps like what we did when we want to find k, but just to give you a hint, because s plus j omega basically is the conjugate of s minus j omega, so intuitively k star is also the conjugate of k. So at this point, I have already found k and k star. So my ys will be like this. K is this one, k star is this one. And then because now I'm interested more on the steady state response, I will neglect the remaining terms. Okay, so this is the response in a steady state condition. If we go back to this response in steady state condition again, I have already identified k and k star, and this will be the steady state response in Laplace domain, of course. So what I can do now, I will sum these two terms. So what I will have this form. It's pretty straightforward to find this form, and then I will sum them all. I will extract this equation. I will lump s with s and j omega with j omega, and this is what I will get, right? Remember again here, k appears in a complex form. When I lump s with s, so what I will get, I will get 2 times real part of k times s, because k plus k star is basically 2 times real part of k. Similarly, when I lump j omega with j omega, I will have, let me write it here to make it simpler. So if I lump s with s, I will get k plus k star s, right? My hand drawing is pretty bad here because I'm using my mouse here, plus k minus k star, right? Times j omega. Please take a note that I'm only writing the numerator here. K plus k star is equal to 2 times real of k, of course, right? And this one, k minus k star, what I will get, I will have plus, of course, imaginary of k j, right? Because k is equal to real k plus imaginary k times j, and then I still have to multiply it by j omega, right? J times j is equal to -1. That's why at the end I have negative sign here. Okay, so what is next? What I have to do then, if I want to find the steady state response in time domain, let me now erase it first. What I will do then now, after I get this steady state response in Laplace domain, what I have to do next is to convert it back to time domain. I just have to refer to my Laplace table. S over S squared plus omega squared in time domain is equal to cosine omega t, while omega over S squared plus omega squared is equal to sine omega t. You can check your Laplace table. Now what I'm going to do, I will make use again this trigonometry identity. If I have this form, n cos omega t cos theta minus sine omega t sine theta, it will be equal to n cos omega t plus theta, where n is equal to, if we look at this, cos theta is analogous to this real part of k, while sine theta in my case here is equal to n sine in this case, if I can repeat it again, n cos theta is my 2 times real k in here, while n sine theta in my case here is equal to 2 times imaginary k here. I can solve the value of n and the value of theta here. I just simply divide this, the second equation, with the first equation, then I will end up with tangent theta equal to imaginary k divided by real k, and then I can find theta accordingly, and then same thing, I just have to solve these 2 equations. I can find n equal to 2 times the magnitude of k. So what I'm going to do then next, I will rewrite this steady state response equation into this kind of form. So my response here now, the steady state response will be equal to this one, right? And then what? I know k is equal to this, so magnitude of k then is equal to this one, a over 2 times the magnitude of g j omega. Well, the angle of k is equal to angle of g j omega plus phi, right? So I can again rewrite this steady state response. It will look like this at the end. What does it mean? This means if I have a system with a transfer function of gs, and to this system I give this harmonic input where the amplitude is a and the frequency is omega t with any arbitrary phase difference of phi here, the response of this system due to this input will look like this. What is the special thing of this response? If you look at this response, the response is indeed still harmonic, where the amplitude here will be magnified by the magnitude of g j omega, and the response here will have a lag of theta, where theta here is equal to the angle of g j omega. Okay, so this is what frequency response function will tell us for a particular system with a particular transfer function. To summarize again here, analyzing the frequency response function for one particular dynamic system, right? We can have this information. If to this system a harmonic input is given with the amplitude of A and the frequency of omega, by just looking at the frequency response function at that particular omega, we can find the magnitude of Gj omega, which will tell us how the amplitude will be magnified, and the angle of Gj omega, represented by theta here, will tell us how the response will be shifted with respect to the input that is given to the system. Similarly, of course, if I give this kind of input, the response will look like this, right? Okay, so in short then, the steady state response, we are only talking about a steady state response here. The steady state response of a harmonic input to a particular system with a particular transfer function, the steady state response, the magnitude will be amplified by the magnitude of Gj omega at corresponding frequency, and the response will be shifted by this following angle. That's what frequency response function will tell us. To summarize again, if I have a system with a transfer function of Gs in frequency domain, then it will be equal to Gj omega. If to this system I give harmonic input A cosine omega naught t, let's say, the response will be pretty similar to the input, but the amplitude will be just magnified and the phase will be shifted. That's what frequency response function tells us. In the next few slides, I will share some practical information, practical knowledge of a frequency response function. Let's start it by looking at this illustration. Why do we need a frequency response function? What frequency response function can tell us? Basically then, frequency response function will tell us how the system will respond to harmonic input at the steady state condition. So for instance, again here, just for an illustration, I have a system with a particular transfer function, and let's say to this system I give a certain harmonic input illustrated as illustrated in a red function here. The output to the system, depending on the frequency of excitation, the amplitude of the response at the steady state condition, of course, here might be amplified or attenuated depending on the magnitude of the J omega, and the phase might be shifted depending on the angle of the Gj omega. So at one particular frequency, we might have a magnitude of Gj omega that is less than 1. In such, the steady state response amplitude will be smaller than the amplitude of the input, where the phase shift is relatively small, equal to 0, the angle of the GJ omega close to 0, so the response will be like this. At other frequency, we might have this following case, where again the amplitude is attenuated here, but the angle of GJ omega is not equal to 0, so the response will be shifted. As you can see here, the response is delayed compared to the input signal there. The magnitude of GJ omega as well as the angle of GJ omega might be different at different frequencies. So for instance, if to this system, let's say I have a piston here, I give a certain input, then I should be able to see how the magnitude and the phase or the direction of the response at the steady state condition will be at different frequencies. For instance, as an illustration, again here I have a piston here. I give a certain input where the input has a certain frequency here. If I give a specific amplitude in the input at the specific frequency, let's say the frequency is like this, the response apparently will look like this. But if I increase the frequency of the input, it might happen that at different frequency, as it is illustrated by this animation, the output is becoming, the amplitude of the output at the steady state condition here not as large as before, because probably the magnitude of the GJ omega at this particular frequency is attenuating the input amplitude. At other frequency, even at higher frequency, we might have a case where the amplitude of the output, again at the steady state condition, is attenuated further. As you can see here, the amplitude of the response of the output is even smaller than the amplitude of the output in the previous case at different frequencies. Okay, so frequency response function, in short, then it will tell us how the magnitude and how the phase of the response as at the steady state conditions are at a specific frequency at the input side. Okay, so why do we need frequency response function? Why don't we just simply use the GS? Why don't we just simply use a transfer function? The first reason is because frequency response function is pretty straightforward to acquire. If I give you a certain dynamic system and I want you to identify the transfer function, the answer might not be really straightforward. There is no straightforward way to find a transfer function from a dynamic system, but there is a straightforward way to find a frequency response function through an experiment. Why frequency response function? The second reason is also because using frequency response function, as I have already illustrated before, we can easily find the system response at the steady state condition, of course, if a harmonic input is given. The third reason of using frequency response function, because it's pretty common in industries, they prefer always to use frequency response function to characterize the property of a dynamic system than by using a transfer function. As I have already mentioned before, through an experiments, we can easily find the transfer, the frequency response function, and I can show it later to you that frequency response function has a indirect relationship with the transfer function. And the most important reason that is related to this course is that the frequency response function can be used as the best, as one of the best tools to help us in designing a controller. Okay. In the previous slide, I have already mentioned that frequency response function can be obtained experimentally in a pretty straightforward manner. What I meant by that, how to find frequency response function from experimental setup, it's very easy. If you have a system and then you want to find the frequency response function, the magnitude of G, J omega, and the angle of G, J omega, you want to find these two entities. So what you have to do, you just simply have to give a harmonic input to the system at different frequencies, and then you record the response to the varying inputs. So for instance, at the first step, you just keep the amplitude constant. Let's say you just put it equal to 1, and then you excite this system with the harmonic input with the amplitude 1, but at certain frequency. Let's say at the first step you use 0.01 for omega, so you have harmonic input with the amplitude equal to 1, for instance, and then omega is equal to 0.01 radian per second. You excite this system in your lab using an actuator, using a shaker, or by any means with any tools that you might have in your lab, and then you measure the response with a vibration sensor, for instance, and then you measure the response. You measure the amplitude of the response, and then you compare the angle of the response to the input in order to get the phi value, the phase shift there. You take note the magnitude, the amplitude of the response. You take note the phase shift, comparing the response to the input, and then you take down here the ratio of the magnitude of the response to the amplitude of the input, x over y over x, the magnitude of y over the magnitude of x. Take a note there, and then you also take a note the phi value. You do it again iteratively for different frequency. Do the same thing. Find the ratio of the amplitude of the output and the input. Find the phase difference there. Take a note here, and then do it again for different frequencies. So by having this table, you can have the magnitude of G, J omega for different frequency, and then you also have the phase or the angle of G, J omega for different frequency. So this column will tell us the magnitude of G, J omega. This column will tell us the angle of G, J omega. So again, then frequency response function is represented by magnitude of G, J omega and angle of G, J omega. How to represent a frequency response function? As I have already mentioned before, that a frequency response function is represented by two values: the magnitude of G, J omega for varying omega, for varying frequency, and angle of G, J omega for varying frequency omega as well. So technically then I can plot the magnitude of GJ omega as a function of frequency, and I also can plot the angle of GJ omega for different frequency. These two plots basically are the information of the magnitude of GJ omega and the angle of GJ omega, where the horizontal axis is the frequency omega. For the first plot, the vertical axis is the magnitude of GJ omega, or we call it gain, and for the second plot, the vertical axis is the phase or the angle. It can be in degree, it can be in radian, it doesn't really matter. But one thing that we have to highlight here, if we plot the frequency response function, normally the frequency is drawn in logarithmic scale. Okay, for both plots, the magnitude plot and the phase plot, the horizontal axis of the frequency is drawn in logarithmic scale, while the phase here, the y-axis, the vertical axis of the phase plot, is drawn in linear scale, just a normal scale, either in degree or radian, it doesn't really matter. But the gain here is drawn not in a linear scale, not in a logarithmic scale, but it is in dB scale. What is dB? dB is 20 times logarithmic scale, right? So again, once more, the horizontal axis is frequency in logarithmic scale. The vertical axis of phase plot is angle in linear scale. The vertical axis of the magnitude plot is the gain or the magnitude of GJ omega in dB scale. And magnitude of GJ omega technically will tell us the ratio of the amplitude of the output and the input, while the phase plot here will tell us the phase difference between the output and the input. Okay, this slide illustrates how the frequency response function plots, or typically we call it as a Bode plot, will look like for any particular transfer function in our system. You might have this kind of plots. A few things that I want again to highlight here. On a frequency plot, if a gain is constant over a certain frequency range, at the low frequency, this will tell us the system can follow input magnitude. If we have phase equal to 0 over a certain range of frequency, that means system can follow the input direction. So once more again, if gain is constant over a certain frequency range, that means the system can follow the input magnitude all over this frequency range. If phase plot is equal to 0, or let's say it's very small, over a certain frequency range, that means the system can follow the input direction, or in other words, it means that the response of this system will have the same phase as the input that is given to the system. Okay, if the magnitude and a phase response is high for large frequency range, then we will have faster time response. What do I mean by that? If, let's say, at low frequency, here, at low frequency, the magnitude and the phase, I do not illustrate the phase here, is constant but high for a large frequency range. So if the range of this flat gain is large, so if we have a larger band that has this phenomena, the larger the band, the larger the frequency band, the faster the response of the system to a particular input. So this feature will tell us how the system will respond to any particular input. I have a few questions here. The input R comprises a slow changing signal superposed with a fast changing signal. So I have an input. The input here is not purely harmonic, but instead my input here is a combination of two harmonic signals. The first one has a slow changing signal, while the second one is a fast changing signal. How does this does a system with output of C1 and C2 represent a system capable of high fidelity? Or in other words here, does this output will tell us whether the system is capable to follow the input or not? You can assess it by looking at the response at two different frequencies. Frequency response function is an analysis of a system capability to follow signals with different frequencies. Of course, when the angle is pretty large, let's say, that means the system cannot fully follow the input. If there is a significant phase lag to the response, that means the system cannot really follow the input. The response always lag behind the input. And let's say if the magnitude plot is pretty small at a certain frequency, that means also that the response cannot follow the input. When we give a large amplitude in our input to the system, then apparently the response is, the amplitude of the response is attenuated significantly. That means the response doesn't have significant amplitude compared to the amplitude in the input. So the response cannot really follow the input of the system. Okay, this slide concludes our introductory discussion in frequency response function. In the next video, I will describe a bit more detail on how we derive frequency response function from system and how to sketch the magnitude plot as well as the phase plot of the Bode diagram for a particular dynamic system.